Hi everyone, this is Mrs. J. Today we're going to learn about the inverses of simple quadratic and cubic functions. Before we get started, I have a quick warm-up for you guys. This should be a review from previous units, so pause the video and give it a try, and when you're ready you can hit play to check your answers. Alright, so go ahead and check your work here. So remember, the general process of finding an inverse is swapping the position of x and y and then isolating y. So our inverse function, it would be 5x minus 1 all over 2. And we can confirm that by doing this composition of function. Here I did f of f inverse of x, and so when you plug this into your original function, you should end up with x if you did it correctly. And then for part B, you can see our inverse function is negative 4x plus 28 all over 3, and you can confirm that by doing your composition of functions. So today we're going to be finding inverse functions of quadratic and cubic models. So just a quick reminder, an inverse function is really just a function that undoes the effects of another function. By definition, as we did in the warm-up, f of f inverse of x should equal x, or f inverse of f of x should equal x. So when you plug one into the other, it results in an x because the operations undo each other. A few other facts about inverse functions, generally speaking. You saw when we're solving for the inverse function algebraically, you swap x and y in the equation and solve. If you have coordinates of your original function, you can swap the x and y coordinates to find coordinates of your inverse. Another way of thinking of that is swapping the domain and range. And graphically, an inverse function is reflected over the line y equals x because, again, x and y are swapped. So here you can see two relations that are functions. So if your original function, this is the domain and this is the range, look at the domain and range of your inverse function. They are literally swapped. They still connect, the two values still connect. Instead of b1, it's 1b. Instead of a3, it's 3a. And instead of c2, it's 2c. Again, just the domain and the range are flipped. And here's a graphical example of what the inverse function looks like. So down here on the bottom is f of x, and this would be what the inverse function looks like. So you can see it has been reflected over this line y equals x. So there are two types of functions, and each type does have a different implication for what the inverse will look like. So this first type of function here, every input has one output, which makes it a function, and additionally, none of the outputs are shared. So this is called a one-to-one function. So when you have a one-to-one function, imagine you swap the domain and range. The inverse will be also a one-to-one function. So when you have a one-to-one function, we can know for sure that the inverse is also a function because every x will only have one y. Now, if you look at this second representation of a number relation, this is a function. Every x only has one y. This x has one y, this x has one y, so do these. However, you'll see that one of your y values is shared by two x's. Again, this is still a function. It's simply a one-to-many function. Now, when you have a one-to-many function like this, imagine what happens when you swap the domain and range. For this input, you'll have two different outputs. So when you have a one-to-many function, we can conclude that the inverse is not a function. So when you have a one-to-many function and you're finding the inverse, you need to do a little extra work to make sure that the inverse is also a function. And we'll show you how to do that in this next example. Okay, so one of the most common functions we work with is a quadratic function. And a quadratic function, as we know, is a one-to-many function, right? The graph looks something like this. So although it is a function, it passes our vertical line test. It fails our horizontal line test, which is what we test for a one-to-many function. So this inverse, if you just swapped all the x and y values, the inverse would not be a function. So what we can do to help us avoid this situation is we can restrict the domain of our original function to turn it into a one-to-one function, so then when we find the inverse, we know that the inverse will also be a function. Okay, so when you're doing this with a quadratic, you can actually restrict it in two different ways. We could either you start at the vertex, and we could either take everything to the right of the vertex or everything to the left. Either way is fine. So for this one, let's restrict, and we should state what we're doing. We're going to restrict the domain of f of x, which is the original function, to everything 0 to infinity. So everything from our vertex moving to the right. So in red, this is the portion of our graph that we will use. So from here, now that we've had this restriction of our domain, now we can find the inverse, and we can find it algebraically. So we're still going to swap x and y. So we have x equals y squared, and then instead of taking the plus or minus square root, all we need to do is just take the positive square root. So y equals the square root of x. Again, usually when we take the square root, we would take the plus or minus square root of both sides. Here, we'll just take the positive square root, and this is going to be our inverse function. We can confirm that, as it says in the directions, using our composition of functions. So let's do f of f inverse of x. So that would be this, so the square root of x plugging in here, so squared, which equals x. So this confirms that they are in fact inverses, and now we're going to graph it. So a few different ways we can go about graphing this inverse. We can take the x and y values that we see here, and we can actually just swap the x and y values. So we see the coordinate 0, 0, so that will stay 0, 0. I'll do the inverse in green. We have the coordinate 1, 1, so that will stay the same as well. And then here we have the coordinate 2, 4, so that means we're going to plot the coordinate 4, 2. So we can do that right here. So it is going to look something like this. Another way of approaching this, again, is reflecting your graph over the line y equals x. So here's the line y equals x, and we're simply reflecting this red portion of our graph over the line. So in red, that's going to be f of x, and in green, this is f inverse of x. So there you have it. So this is a basic example because it's the parent function of our quadratic. So now we're going to try a few that are a little more complex. All right, so here we have another quadratic function. It is in that vertex form. So again, we need to restrict our domain. So we can ensure that this is a one-to-one function, which would then ensure that our inverse is also a function. So to do that, let's start by finding the vertex of f of x. So our vertex is going to be at 3, 7, which means I can restrict everything to the right of our vertex by simply saying everything 3 to infinity. So our domain, so f of x domain is going to be everything from 3 to positive infinity. So we can graph that portion of our graph now. So again, our vertex, I'll do it in blue, will be at 3, 7. So that's right here. And then we can look at our a value, which is -2. So our vertical growth pattern will be -2, -6, and then we could do -10 as well. That will go off our graph. So it looks something like this. And again, that's just our 1, 3, 5 growth pattern adjusted for this vertical stretch and the reflection. So here's f of x. Let me label it. And now we can find our inverse algebraically. So let's swap x and y. So x equals negative 2 times y minus 3 squared plus 7. So we can subtract 7 and then divide by negative 2. All right, from here we're going to take the square root of both sides. So it leaves us with y minus 3 equals the square root of x minus 7 over negative 2. And then we will finish by adding 3, and that will be our inverse function. So I know right here you're probably thinking, oh wait, I can't take the square root of a negative number. But remember, we don't know what x is. So if x is a number that makes our numerator negative, then our denominator will also, then the denominator will turn it into a positive, so we can take the square root. So depending on what x is, this square root will be defined sometimes, and then sometimes it won't be defined, which is why these graphs do have a restricted domain. So this is okay because, again, we don't know what x is. X could make this entire thing positive. So let's confirm that this is correct using our composition of functions. Let's do f of f inverse of x. So we have negative 2 times square root of x minus 7 over negative 2 plus 3 minus 3 squared plus 7. So here, the plus 3 minus 3 will cancel out. And then here, I'm squaring a square root. So what I have next is negative 2 over x minus 7 over negative 2 plus 7. And then here you can see the negative 2's are a common factor, leaving me with x minus 7 plus 7, which is just x. So we've confirmed that they are, in fact, inverses. So if I go to graph this, again, I can reflect it over this line y equals x, like this. Or an easier way to do this, because sometimes it's kind of hard to visualize where these reflections will be. Some of them we can do, like this point is going to be here. But we can also just take the coordinates and swap x and y. So instead of being at 3, 7, it's going to be at 7, 3. So 2, 4, 6, 7, 1, 2, 3, like this. This coordinate, instead of being at 5, negative 1, it's going to be at negative 1, 5. So it'll be right here. And our graph is going to end up looking something like this. So you can see this is reflected over the line, y equals x. Again, I think the easiest way to do this is just to take the x and y values from your original coordinates and then just swap x and y. And here's f inverse of x. All right, we're going to try one more together. So here again we have a quadratic equation. We will need to restrict the domain from the vertex on to make sure it's a one-to-one function. But here, so we could use the vertex formula to find the vertex, but when we go to solve algebraically for the inverse, it will actually be much easier to do if we have it already in vertex form. So let's rewrite this equation in vertex form. So remember, to do that, we're going to take our constant and we're going to move it to the other side. And we are going to need to complete the square for this. So let's factor out a 3, leaving us with x squared minus 2x. And then I need to complete the square here. So you take your b value, you divide it by 2, and you square it. So our magic number is 1. And I know it looks like we added 1, but we actually added 3 times 1. So I need to add 3 to the other side. So y plus 8 equals 3 times x minus 1 squared. And now we have our vertex form. So we can see that this quadratic has a vertex at 1, negative 8. That's the vertex. So we're going to restrict the domain to everything to the right of our vertex. So the domain of f of x is going to be 1 to positive infinity. So let's start with 1, negative 8, right here. And for this one, our A value is 3, so remember we take our 1, 3, 5 vertical growth pattern and we adjust it for that vertical stretch. So it's a 3, 9, 15 growth pattern. So you can go up 3 over 1, and then you can go up 9 over 1, and then you could go up 15 over 1 if you wanted an additional point. So here we have a pretty stretched out graph. It looks something like this. And now we want to find the inverse algebraically, and then we're also going to graph it. So we're going to go from this version of our equation. We're going to swap x and y. So we have x equals 3 times y minus 1 squared minus 8. So again, here I'm going to add 8 and divide by 3. Then we can take the square root of both sides. And in this case, we'll just take the positive square root, and then we'll add 1. And that will be our inverse function. So f inverse of x equals the square root of x plus 8 over 3 plus 1. Let's confirm that using our composition of functions. So let's do f of f inverse of x. So when I'm doing this, I'm actually going to substitute it into our vertex form of this equation. So right here. So we have 3 times, and then we can put f inverse of x, so the square root of x plus 8 over 3 plus 1, minus 1 squared minus 8. So again here, the plus 1 minus 1 will cancel out. The square and the square root will cancel out, and then the 3 and the 3 will cancel out, and then we're left with just x plus 8 minus 8. So that does equal just x. So that confirms that they are inverse functions. And then to graph it, I'm going to zoom in here. Again, we're just going to reflect it over the line y equals x. So we know we have this coordinate here. Here we can take the coordinate 2, negative 5, and we can do negative 5, 2. And here we can take our vertex, which was at 1, negative 8, and we can do negative 8, 1. So it look like this. So our inverse function looks like this. And notice that at the line y equals x, we do have an intersection. So they should cross exactly at the same point. So here's f inverse of x, and here is f of x. So this one definitely a little bit more work because we do need to rewrite our function in vertex form. So 1, we can restrict our domain, and 2, we are able to solve algebraically for the inverse. All right, so I have one for you to try on your own. Pause the video and give it a shot. It is a little bit more complex with the rewrite. There will be some fractions, so just plug through it, and we'll check your answers in just a few moments. All right, go ahead and check your work here. So when you are completing the square for this problem to rewrite it, so remember you take your b value, you divide it by 2, which is 3 over 4, and you square it. So it's 9 over 16, which I added here. But you're actually subtracting 9 over 8, because you have the negative 2 times 9 over 16. So you're actually subtracting 9 over 8. So it gives you negative 17 over 8 on the left. And then when you factor this trinomial, the trick here is that the number inside your factor is always going to be b over 2. So b over 2 in this case is 3 over 4. So it's no coincidence that the b over 2 value is the same as this value. And then you can add 17 over 8 back to the other side. So you can see our vertex is at negative 3 over 4, 17 over 8, which is right here. You can kind of estimate where that is on your graph. So I'm going to restrict my domain to negative 3 over 4 to infinity, so just the right side of my graph. And then I found the inverse algebraically here, and I tested it to make sure that it works using the composition of functions. Now to graph the inverse, I found a few other nice coordinates from my original function, so from this version. So I plugged in 0 and I got 0, 1. I plugged in 1 and I got -4. So then you can take those and you could use the, you can swap x and y. So I plotted, I estimated where that my new quote-unquote vertex would be, and then here I have 1, 0, and here I have -4, 1. So you can find other points from your graph, and then you can just swap x and y to find your inverse function graph. So now we're going to try finding the inverse of a cubic function. So a cubic function is actually a one-to-one function. If you remember what something like this looks like, well, the parent function, right, looks something like this. 2, 4, 6, 8. So this is our parent function. So you can see that our parent function, I'll call it p of x, it is a function. It passes our vertical line test, but it also passes our horizontal line test. So it is a one-to-one function. So that means when we're finding the inverse, we don't need to worry about a domain restriction. The inverse of this type of function will also be a function. So if we were to graph this, remember this is just our cubic function shifted down 9. So I can take these 3 coordinates and I can just shift them down 9. It's the easiest way to graph. So let's do that first. So f of x is going to look something like this. And we have our transformed coordinates. So we have 0, -9, and then we have 1, -8, and we have -1, -10. Now we can find our inverse algebraically, and then we'll graph that inverse function. So let's swap x and y. So I'm going to add 9 to both sides, and then to get rid of a cube, we take the cube root. So f inverse of x is going to be the cube root of x plus 9. So to check, let's do f of f inverse of x. So we have cube root of x plus 9 cubed minus 9. So here the cube and the cube root cancel out, leaving me with x plus 9 minus 9, which is just x. So we've confirmed that they work. And now to graph it, we could reflect it over the line, y equals x, or we could just take a couple coordinates that we know and we can swap x and y. So instead of 0, -9, we can do -9, 0. And we can do -8, 1. And we can do -10, -1. So we get something that looks like, it will end up looking like this. So again, we still need to make sure that it's reflected over that line y equals x, but it's going to look something like this. So instead of being kind of a more vertical looking graph like this, it's going to look more horizontal. You'll notice that, again, our inverse function is also, well, it's an inverse, or sorry, it's a function without us needing to restrict the domain of our original function. So this is f of x, and this is f inverse of x. All right, so I have one for you to try on your own, so please pause the video and give it a go, and you can check your answers in just a few seconds. All right, go ahead and check your work here. So here's my graph of f of x. So this graph has just been shifted to the right 4 and vertically stretched by a factor of 2. And then I found the inverse algebraically. I double checked using composition of functions, and then I took some values from my original function and then swapped x and y to plot them here. All right, so now I want to take a moment to just look at a couple of real-life examples of when an inverse function might be useful. So let's take this example, d of t equals 16t squared, which is the actual model that models how far something has fallen. The output is that distance, given how many seconds it has fallen for. So your input is how many seconds, and your output is the distance. But what if you wanted to model how long an object is falling in terms of how far it has already fallen? So what if you wanted your input to be the distance and your output to be the time? That's when you would use the inverse function. So for this, you would actually, well, first we do need to restrict the domain of our original function. So the domain, we're going to restrict to 0 to infinity, because this has an inverse, or a vertex at 0, 0. And now, instead of actually swapping d and t, we're going to keep the variables the same. We're just going to solve for t. So we'll divide by 16, and then we'll take the square root of both sides. So this model we could use to for an input of distance, so we can plug in any distance that the item has fallen, and then we can figure out how long it has been falling for. So again, using the inverse can be useful depending on what you would like to be the input and what you would like to be the output. So another really common model we use is this right here, a equals 4/3 pi r cubed, which models the surface area of a sphere in terms of the radius. So this is when you have the radius as the input. So you input the radius, and the output would be the surface area. But what if, kind of like the last example, what if you wanted to model the radius of the sphere in terms of the surface area? So what if you knew the surface area and you wanted that to be the input and the output was the radius? So you would find the inverse. So again, I'm not going to actually replace the variables because we would like the input and output to swap. So we're going to solve for r. So we can multiply by 3 and divide by 4, and we can also divide by pi. So we're going to have 3a over 4 pi equals r cubed, and then I could take the cube root of both sides. So 3a over 4 pi. So this is a model that we could use, again, if we wanted the input to be the surface area and the output to be the radius. So here would be, another real-life example of when it might be useful for us to be able to find the inverse. And again, for this one, since the original function is a cubic function, which is a one-to-one function, we don't need to restrict the domain for this problem. Okay, that is all for today's video. Thank you so much for watching.